So welcome to the PALS seminar. Our speaker today is Gergő Gyenizse from the University of Szeged, and he's going to talk about joint results with other people on general Hobby-McKenzie varieties.
So thank you much for the introduction and for the invitation. Yes, this is a joint work in the department. Really, half the department, well, not half, but a third of the department was working on this in the last 1.5 years, and really some results and some questions are longer than that. So maybe some of you have already heard some of this, because there is an open question that we cannot solve for at least 2 years now. So I'm starting with Taylor varieties. Let's start with some, I've seen quite well-known definitions. So by a linear identity, we mean that we have a signature and we have two operation symbols, S and T, of the signature, which are usually the same, but technically not necessarily always the same. And we are plugging in some variables on both sides, which may be different and may be the same, and this will be a linear identity. Also, this is what they call the height one identity. A linear identity is more permissive in that a linear identity can be an absorption identity. So it can say that if we plug in some variables, and let's say, for example, the first two are equal and the last two are equal, let's say for a Fourier term, then it must always give one of the variables, so let's say the first one. So possible linear but not height identities like t, x, x, y, y is always x. So we call an algebra a Taylor algebra if it has an idempotent term of any arity that satisfies a bunch of linear identities in two variables. So they can all these x, y's and xj's are either x or y, and that system must be so that no projection satisfies it. So that means that for each position we must have one identity, like identity when on the left side there is an x and on the right side there is a y. And of course, the variety is Taylor if it only contains Taylor algebras, and in that case, thinking about the free algebra generated by two elements, you can see that the Taylor term is always can be chosen as always to be the same for all algebras in the variety. So there are quite a lot of results about Taylor varieties, and some only work for locally finite case, and some will work generally, so not without the restriction that our variety is locally finite. So in this presentation, I'm distinguishing between these two cases by color. So when I'm using this violet color, then that means that the result is only for locally finite, or at least only known for locally finite case. And when I use the orange color, that will mean that that the result holds in all varieties. So there are really quite a lot of such results, and I will only pick some of them. So first of all, what works in locally finite varieties is that variety is Taylor if and only if it admits a so-called Sigar term. That's the sixth Seri term that satisfies these two identities. And of course, if something satisfies these identities, then it must be a Taylor term. So it's trivial that if something is Sigar, then it's Taylor. But the result is that in locally finite varieties, from a Taylor term, we can somehow get this specific Taylor term. So I think this is a 2010 result. And this is equivalent to a result about graphs. So that is equivalent as saying that if we are taking a variety, taking any algebra of it, and any directed graph that is compatible with this algebra, And by this we mean that the graph as a subuniverse of the direct sphere of the algebra is a subuniverse of the direct sphere of the algebra. So if you take any graph, a compatible graph in the variety, then if it contains a triangle, it must be reflexive. So this condition is called a loop condition. So because it says that if a graph has a triangle, then it also has a loop. And this can be easily seen as being equivalent to the existence of the Siegel polymorphism, because you apply this condition in the free algebra generated by three elements x, y, and z, and the graph field generated by the edges x, y, y, x, x, z, z, x, y, z, z, y. Also, this result has a variant which is harder to prove, but a little bit more commonly used. So Barton and Kozik proved not long after Siegers, or maybe essentially concurrently, that a variety, locally finite variety again, is Taylor if and only if we take any smooth compatible graph that has algebraic length 1, then it must contain a loop. So it's something more general because in the previous point that graph was the irreflexive symmetric triangle on three elements. So this is a more general result, and by that, by this loop lemma, we can get a bunch more conditions that are like this. And the most famous and most commonly used of this is the rare area, or in other words, Forciger stems that says that locally finite variety is Taylor if and only if it has an idempotent Fourier term that satisfies the identity T of x, y, x, z equals T of y, x, z, y, I believe.
Sorry, could you repeat the definition of there is a graph in the variety? What do you mean there is no compatible graph of the variety?
So I mean that compatible graph of the variety, by compatible graph of a variety, I mean that I take any algebra of the variety and I take any diagraph that is compatible with all the operations of the algebra. And I get
Okay.
that graph just as a graph, just as a structure.
Okay.
And
Yeah.
there is something, then I say that it is compatible with the variety.
Okay.
Yeah, we also have a TCT characterization, and locally finite variety is TCT omitting type 1 if it is Taylor. And there is a congruence condition. Locally finite variety is Taylor if and only if the congruence lattice is satisfied this SD meet over modular condition. That means that all the congruence lattices have a lattice congruence such that the classes are modular, and the factor with that congruence is a mean semi-distributive lattice. And I think that most of these conditions are proven to not hold in arbitrary varieties. So I believe even this for general varieties, this will not be equivalent to Taylor, but a little bit stronger. I think well, unless we are somehow changing the definition of type 1, this will not hold. And Kajda proved some years ago that this also doesn't hold. So it's not true that if a general variety is Taylor, then it must also have Siegel stems. And his example was that just take the variety generated by the three weak unanimity identities, and it will not admit Siegel stems, or actually it will not admit any terms that can be expressed by a single linear identity. And I don't even know that a single nonlinear identity can be derived from the W and U conditions. Yeah, this was the violet stuff. Let's go to orange. There are some results that are generally true about Taylor varieties, and oddly enough, there is a strong Markov condition that is to Taylor. So this was also a result from the late 10s, I think 18 or 19, that a variety is Taylor if it has a six-array term that is idempotent, that satisfies these equalities. So it's a double identity because there are three things here that are equal. And we can express this as a graph condition, a loop condition, or really it will be a hyperloop condition. This is not the kind of hyperloop that is a new mode of travel that never happens, but something else. So we can express this as if we take a compatible ternary hypergraph of the variety. By hypergraph, I just mean that a relational structure that has only one relation and that is arity 3. I'm not assuming irreflexivity or reflexivity or symmetry or anything such. So if we take a compatible 3 hypergraph and this contains a rich subset, and by rich subset, I only mean that a two-element subset on which of the 8 possible triples, 6 are in the relation. If this is the case, then it also contains a hyperloop, so an element of the form AAA. So if in that rich subset, the elements that are on the relation are XXY, XYX, XYY, YXX, YXY, YYX. So all the triples that are not loops from this we can somehow find a loop just by a Taylor term. This is also a different characterization that we will use today, is that variety is Taylor if there is no clone homomorphism that goes from the idempotent reduct of the variety to the variety of sets. So one important Markov class that are in a way similar to Taylor, in a way is the most similar Markov class to Taylor, and that way will be, which I will talk about because there are some ways in which it is very different from Taylor, is the Markov class of Hobby-McKenzie varieties. So we will call an algebra Hobby-McKenzie if it has an idempotent term that satisfies a set of two variable linear identities. So far, it is the same as Taylor, but we require not only that it must be a non-trivial set of identities, but we require also that it is not satisfied by any semi-lattice term. So let's see this example. So we have three linear identities, and this will and that term satisfying this T will be an HM term, Hobby-McKenzie term, and it will define a Hobby-McKenzie variety. Why is this so? So if you only look at let's say the first two identities, those can be satisfied by this is already a Taylor term from the first two identities, because only the fourth projection satisfies the second one, and that doesn't satisfy the first one. So only by the first two we can see that this is a Taylor term. But with these two identities only, it's not a Hobby-McKenzie term, because if we take the meet, because there is a semi-lattice term that satisfies this. So let's take the meet of the first two variables in a semi-lattice. Then, so in a semi-lattice, let's define T as for every term that outputs the meat of the first two variables, then it will satisfy the first, and it also will satisfy the second, but it will not satisfy the third. So if we take the whole set, then it will result in an HM term. If we only take two identities of the three, then it will not result in an HM term. What do we know about Hobby-McKenzie varieties? Maybe a little less than for Taylor varieties, so it's not as important a class. And there are things that are, again, only true for locally finite, and there are things that are general. So the thing for locally finite is that we have a TCT characterization, and that characterization is very nice. This is the omitting 1 and 5 class. So that means this is a little less than congruence modular, because congruence modular is omitting 1 and 5 and no tail, and here we can have tails. It's also less than the congruence joint semi-distributive, because that's omitting 1, 2, and 5. This is only for locally finite, and there are some that are general. So the first one is that the algebra is that there is a non-trivial lattice identity that is satisfied by the congruence lattice of any algebra in the variety. The second is, which is very similar to a condition for Taylor, is that the congruence lattice of any algebra is SD join over modular. So in the Taylor case, it was SD meet over modular. The odd thing is that here there is no difference between the locally finite and non-locally finite case. This holds for general varieties. And again, something that is similar for the Taylor case is that there is a clone homomorphism that goes from the idempotent reduct of the variety. No, it should be there being no clone homomorphism that goes from the idempotent reduct of the variety to SL. So SL is the variety of semi-lattices. So like it was no clone homomorphism here, and also it should be some here. So let's look at some well-known Martsev classes, and I will order it by reverse inclusion hierarchy. So if something is, if a Martsev class is above another, then that means that there are less algebra satisfying it. So what is on the top is the strongest Martsev condition, and what is on the left is the weakest Martsev condition. So so what's on the bottom here in this picture is the class of all varieties. So let's say this is the this can be defined by the Martsev condition x equals x, and on the top only the trivial varieties that can be defined by x equals y. So what we are interested today is this point Taylor and this point Hobby-McKenzie, and you can see the relation for other classes. So sorry if your favorite Martsev class is not on this picture, because there are some other important things. And I will tell you about some maybe not so important things, but important for this talk, that are not on this picture. But I think that this more or less covers the basics. So this is just a poset. Yeah, it's actually a lattice looking at it like this, but we'll only consider this a poset right now, because when we are talking about lattices, the rules are a little bit different. So here we have to talk about this interpretability lattice. So we are I think this interpretability lattice was introduced by Taylor in the 70s. So we are saying that a variety V1 is interpretable into a variety V2 if there is a clone homomorphism from the term clone of V1 to the term clone of V2. Informally, that means that any Martsev condition that is satisfied by V1 is also satisfied by V2, and this is true not only for Martsev conditions, but infinite Martsev conditions. So this is a reflexive and transitive relation. We can define anti-interpretability as as an equivalence on varieties when two varieties are equivalent if both are interpretable to the other. We can factor by this equivalence and we get a poset that can be proved to be that is proved to be a lattice. So this is a big extension of this picture, because here we only have some Marcev classes, and this would contain all Marcev classes and even a little more. So informally, you can think about this interpretability lattice as the lattice of strong Marcev conditions. Only informally, because strong Marcev conditions must be finite, and here we can have varieties that are quite infinite. If we want general Marcev conditions also, then instead of the interpretability lattice, we can take its filter lattice. So strong Marcev conditions are characterized by a finite set of identities, and general Marcev conditions are a union of descending chain of Marcev conditions. And it's not hard to see the lattice that this is a lattice, because this can be obtained as the lattice of closed set. So for Galois connection between algebras and sets of identities. So we take the correspondence between algebras and sets of identities. The correspondence will be that the algebra satisfies that set. This will result in a Galois connection, and the lattice of closed sets will be this lattice. And we just mentioned this, that there are some cardinality problems. So there are more varieties. So all the varieties don't form a set. So it's a little tricky about talking this lattice, because its underlying set is not really a set, but this can be waved away by some tricks, as taking maximal cardinalities or maximal number of terms in the signature and some stuff. I like to wave away these problems. So we can talk about the interpretability lattice, like it's one concrete thing. And we call a Marcev class, or a Marcev condition, a prime condition, if it represents a joint prime filter in the interpretability lattice. So informally, we say that L will be a prime Marcev condition, or a joint prime Marcev condition, because we can look at the meet primes also, but that's a whole other thing. If whenever K1 and K2 are such Marcev conditions, we can say that we can suppose that these are strong Marcev conditions, such that there is an algebra satisfies K1 but not L, and also an algebra satisfies K2 but not L. Then there is an algebra satisfies both K1 and K2 but not L. So if L can be deduced by K1 and K2, then it can be deduced by either K1 or K2. So let's see some examples. First of all, what is on the top of this picture, and also the top of the interpretability lattice, the class of trivial Marcev classes, that will be a prime condition. And this is not hard to see why. So suppose that K1 and K2 are such that there is an algebra satisfy K1, but not this. That just means that there is a non-trivial algebra that satisfies K1. Let's say that its size is kappa 1. Also, same for K2, there is an algebra of size kappa 2 that satisfies K2. Also, if something satisfies a Marcev condition, then all these direct powers will satisfy that Marcev condition. So there is an algebra of size kappa 1 to the aleph nu kappa 1 kappa 2 that satisfies K1, and also an algebra of that same size that satisfies K2. And then that means that on a set of this cardinality, we can define terms that satisfies K1 terms that satisfy K2. We are putting those two together. We obtain an algebra that is that satisfies K1 and K2, but is still not prime. So this condition holds. On the other hand, it's quite easy to see that congruence distributivity is not a prime condition. So look at this. Look at this figure. So CD is here. Congruence modularity is here, and let's say congruence meets semi-distributivity here. So in that picture, it seems like CD is the join of CM and SD meet. And actually, it indeed is the join of those two. So variety is congruence distributive if and only if this congruence modular and congruence meets semi-distributive. This is because of the simple fact that a lattice itself is distributive if it is both modular and meets semi-distributive. There are other joins here. There are other similar joins here that are indeed joins. So Pixley is kind of defined as majority join with CP. But I don't think it will be true. I don't think it will be true that CD join CP is Pixley again. So what do we know about the primeness of these Markov conditions? So I believe that the current picture is the following. So there are versions of this class because we can consider primeness not only among general Markov classes, so for general varieties, but we can restrict to idempotent varieties, or we can restrict to locally finite varieties, which will result in a different picture. So I think that the color of this vertex will be different for local, no, for idempotent. Maybe for locally finite also. So for those it will be green, and here it is red. So in this picture, green means that is known to be prime condition. Red means that is known to not be a prime condition, and black means that we don't know. At least I don't know whether it's a prime condition or not. I think CM is long conjecture to be prime, but we still don't know. I have no idea about SD meet over modular, and yet this picture kind of suggests that 3 permutability is the join of CM and M permutability, and this I think it's quite likely to be the case. So I believe that this is probably red, but I don't know. This may be green. So what I want to talk about is this green dot and this green dot. So this green dot is trivial. The greenness of the trivial dot is just told you. CP is not easy to prove that this is green. It's also not that easy to prove that this dot is red. It's quite easy to prove actually that this line is red. That is a very simple example that shows that this line is red. So the example is that we are taking minority. So minority as a Markov condition. So we have a ternary term that if we input 2 x's and 1 y, then it will output y. That's one Markov condition, which is not SD meet, and we are joining this together with binary commutative idempotent terms, and we can actually derive easily a majority term from this. But let's go first for Taylor, and then I will switch to Hobby-McKenzie. So the greenness of these two dots will be rather similar. First of all, an aside. So Taylor is the weakest non-trivial idempotent Markov condition, but not the weakest overall non-trivial Markov condition. So there are elements in the interpretability that is outside of this that are incomparable to Taylor, and I will give you such an example. So consider the strong Markov condition that derives from these identities. So we have two terms, a binary term and a unary term. They satisfy these identities, so F will be idempotent by G. Not necessarily, and it is not that hard to prove that an algebra satisfies this Markov condition if and only if all compatible relational structures of it can be expressed as a direct square of another relational structure. So that means that if an algebra satisfies this Markov condition, then the cardinality of any algebra in that variety must be a square number. So, for example, it cannot have a two-element algebra, and that means that Taylor cannot imply this Markov condition, because it's of course possible that we have a Taylor variety that has a two-element algebra. But also the other way around, this condition doesn't imply Taylor, because I think if we are taking a digraph, let's say the digraph C, this digraph C. So this is just a reflexive circle, and that is and take is direct square. Then on this direct square, because it's a direct square, we can define these operations. But in the direct square, we cannot. It's not hard to prove that we cannot define Taylor operations. So this is a condition that's outside Taylor. So actually, there is life outside Taylor. There are interesting Markov classes outside Taylor, but not too much. Not too much, and that was our theorem that we proved, that if a variety is not Taylor, then we can take this graph C, and from this we can derive a new graph C kappa for a cardinality kappa, that will be compatible with that variety, if that variety is not tailored. So that basically means that if we have Markov condition that is not tailored, then it can be obtained by looking at these so-called direct decomposition operators. So these are not really decomposition operators, but power decomposition operators. So we call this a direct sphere decomposition operator, because it will only work for direct spheres. But if a variety is non-tailored, then it can be satisfied by terms like this in a way. Only in a way, because there are some infinitary stuff going on here. So I will sketch the proof of this theorem. So it will be three pages here. In our paper is rather longer, so I will liberally skip details. So suppose that we have a variety that is non-Taylor, and take this digraph C that I've just showed you, and field generate a digraph F from this. By that I mean that take the free algebra generated by three elements x, y, z, and in this consider the graph generated by the edges xx, yy, zz, xx, yy, zz, xy, yz, zx. That will be the digraph field generated by this digraph C. This will not be a connected graph. Actually, it will have several components, or really as many components as there are unary terms in V. So the underlying set of F will be the set of ternary terms in V, and two ternary terms will be in the same connected component if and only if the unary product of the two terms are the same. So we will have components. We will have one component corresponding to any unary term of V. One of the unary term of V is the identity, and what corresponds to the identity? The the set of idempotent ternary operations of V. So we will define an equivalence on underlying set of this graph. Two elements will be in the same. So C is this equivalence. So equivalence will be C equivalent if and only if there is an epimorphism from the graph F to C. So graph homomorphism from F to C that maps ONV to the same element. So this C can be proved to be a congruence of the polymorphism clone of F. And we are using the fact that we are in a non-Taylor variety, so that means that we have clone homomorphism from the idempotent reduct of V to set. And we can understand this in graph theoretic language, this clone homomorphism. So what does this clone homomorphism mean? This clone homomorphism will map any idempotent ternary term to a projection, either X, Y, and Z. And we can look at this that, an idempotent ternary term is an element of the identity component of F, and we are mapping it to either X, Y, or Z, which are elements, which are ternary terms, the projections. So this clone homomorphism can be seen as a graph homomorphism from a component of F, the component corresponding to the idempotence to a subgraph of that component, which is really the free generator C. And also this, because clone homomorphism keeps projections, this will be a retraction. So this homomorphism will fix for the projections X, Y, and Z. And this means that X and Y are not collapsed. So look at the whole picture. We have that we are starting from that graph F. We factored it by a congruent C, and we get that graph K, which is still a compatible world graph in V, and all these components are subgraphs of a direct power of C. Not necessarily induced subgraphs, but subgraphs. So all the components of K live inside the C power, and we are just saying the union of these C powers, and that will be a direct G. So G will be a disjoint union of some C powers. You can get the components. Each component corresponds to a unary term, and in each component, if you use that unary term, then U X X X, U Y Y Y, U Z Z Z, those are ternary terms, which may be different or non-different. So if they are the same, then it's not hard to prove that the component is trivial. If they are distinct, if two of them are distinct, then they are pairwise distinct, and they form a subgraph again isomorphic to C. This will be the diagonal of that component. Now we can take an operation that is compatible with the graph K, and K is not a connected graph. So an operation will work piecewise. So to tell how an energy operation on K works, we take connected components K1, K2, Kn of K, and F will F will map a tuple such that the i's coordinate is from ki to some other connected component, let's say kt. So F can be put together by pieces like some homomorphisms from k1 times k2 times kn to some kt. So we are just looking at this little part of F. And this one part will be denoted by overline F. So overline F maps to kt, and kt was a subgraph of a C power. So a map that has image in kt will have several components, and those components map to C. So overline F have several components. Both of them are mappings from k1 times kn to C. But k1 to kn, if they are non-trivial, if they are trivial, then we don't care. So if they are non-trivial, then they will have diagonals that are isomorphic to C. So each component of overline F restricted to the diagonals. So the diagonal of this times diagonal of this times diagonal of this. This will be graph homomorphism that grows from a direct power of C to C. And that graph C is a very innocent graph that is that it has not too many polymorphisms. Actually, it only has unary polymorphisms. So all the polymorphisms of this graph look like that we are input n elements and we are taking out the ith element, and maybe we are doing some automorphisms on that. But they are each essentially unary. That means that if we take the restriction of, so if we take the component, the restriction of the component of overline F, that will depend on only one variable. And non-trivial, but we can prove that overline F, or really not overline F, but the component of overline F itself can only depend on that this one variable. So it will be like, take this variable and apply this automorphism to the graph. And this will give a natural extension of F to a polymorphism of G. So piecewise, we can extend F to a mapping between the C powers that the components of K live in, and from a polymorphism. So polymorphism of K, we can get a polymorphism of G, and importantly, this can be done in a canonical natural way. And this is important because this being natural, or I think that we needed this. This is a unique extension. By this, it's easy to prove that this extension is a clone homomorphism from pole K to pole G. So K was a graph that was compatible with V. It satisfied the Maltsev condition induced by V. And if we are taking a clone homomorphism, then the image will still satisfy that condition. So pole G satisfies the Maltsev condition induced by V, so G is compatible with V. And G is a disjoint union of direct powers of C. So we started from a non-Taylor variety, and we get a disjoint union of direct powers of C that satisfied that Maltsev condition. And by some PP constructions, we can canonize that. So this is a graph that has components that are direct powers of C, and it can be seen that it can be canonically chosen as this disjoint union of powers of C. And for the other direction, so the other direction was that if this is a compatible digraph, then it cannot, of a variety, then it cannot be tailored. It's easy to see because C is a retract of C kappa. So by retract, I mean that there is a graph homomorphism from C kappa to C, and another graph homomorphism from C to C kappa, such that if I do first E and then F, then we get the identity on C. And retraction preserves linear identities. So if a linear identity holds on C kappa, then it must also hold on C. So if there was a Taylor operation on C kappa, because Taylor is a set of linear identities, then it would also be on C, but there is nothing on C. So just unary operations. So this cannot be. Oh, so we have done this, I think, maybe 1.5, 2 years ago, and we from this we wanted to go to Hobby-McKenzie, because this seemed to be the logical continuation. And first we saw that we only have to change the graph. So instead of C, we are adding a backwards edge. We get this new graph which we called D, and we wanted to prove that the variety is Hobby-McKenzie if and only if there is no cardinality such that this D kappa that we obtain the same way from D as we got C kappa from D, then this is compatible. And again, the one direction is easy if a variety is Hobby-McKenzie, then it cannot be compatible by such graph, because again, D is a retraction of D kappa. There are no Hobby-McKenzie operations on D, and that's it. But the hard direction we couldn't do. So the proof did not carry over to the hard direction somehow. But when we changed D to something else, then it did carry over, and I have to say that I still don't know why that was. So it's something non-trivial. Instead of this graph D, we had to have a hypergraph S. So consider this hypergraph S. This is basically the graph of the mid semilattice of the mid Boolean semilattice. But we could prove that a variety is Hobby-McKenzie if and only if S kappa derived the same way from S is incompatible with the variety for any kappa. So it's how much time do I have? So how long are these talks?
The talks are 50 minutes, but you started a little bit late, so maybe 5 more minutes.
5 minutes left?
Yeah, 5 minutes, yeah.
All right. So this the proof of this theorem is much similar. So I have this here. I will not go over. We are doing the same stuff with S and semilattice instead of the graph C. And towards the end of the proof, it goes into something that it is a little mysterious to me, but it works. I don't have time for this. So it's a harder proof because we had to do some unexpected stuff. But what I want to talk about, that we believe that with this technique we can get something else. We didn't think this through yet, but we don't know what is really special about semilattice and this graph. So we try to do the same thing instead of with abelian groups. And we have the following idea. Take the following keycap graph. Now we need 4 variables. So again, on Boolean, we take the graph of the ternary addition. And if we can squeeze out a very similar proof for this A, then we would get the following. For any variety where the following are equivalent, there is a clone homomorphism from the idempotent reduct of V to the temp clone of Z2 plus. And second, there is a cardinality kappa such that A kappa is compatible of the variety. So I actually don't really know if this is a nice condition here. So this first condition may be not an interesting must-have condition. That's one. And the other thing is that we couldn't yet prove this conjecture. We really didn't do a serious crack at it, but it's something that is an open thing, and that seems to me quite interesting. And maybe you can do the graphs of some other operations here. It seems important that you do it on a binary set. And maybe and it seems that it matters that semilattice had the odd property that the clone is the same as its own centralizer clone. But serial addition has the same property. Not really. The centralizer clone, I believe, contains a two-array addition, but something similar. So maybe it doesn't even work for this. Maybe it only works. Maybe it works only for this. We don't know. And one other thing that I wanted to talk about is an open problem. I think we have talked about this with Keith almost 2 years ago, and it's still open. And it quite matters me because I'm not even sure that is true. I mean that I'm 50-50 on whether this is true. This is about graph conditions for Taylor and Hobby-McKenzie. So what do I mean by a graph condition? That's a condition that can be expressed only by the graphs admitted, only with the compatible graphs of the variety. So first, some terminology for graphs. Take a digraph by same with the reflexive and transitive closure of the relation that of the double edge relation. So we are calling this extreme connectivity. 2 elements of the digraph, 2 vertex will be extremely connected if we can connect them by double edges. We are factoring out with this equivalence, and we are calling the resulting graph the derived digraph of H. We don't actually usually do this. I just do this for this presentation. And we can recursively define the nth derivative. And we proved that, and this is orange, so this is for arbitrary varieties. A variety is Taylor if and only if for each natural n, that is a natural k, such that if we take the reflexive cycle of length n, fully generate a graph, so that's a graph compatible with a Taylor operation, then if we are taking this derived series, then it will then there will be a point when it results in a trivial graph. And actually, I believe that k can be chosen as n-1. So this is a nice and absolute graph condition that describes Taylor. And for HM, we have a similar condition, but we could only prove that for locally finite case. So the condition is that if we take a strongly connected component graph and we are doing this derivation operation, then we get the trivial graph. So if we take a digraph that is strongly connected, from each vertex there is a directed pass to any other vertex, then this is also extremely connected. So from between each two vertices there is a pass of double edges. So this condition seems to us to describe Hobby-McKenzie. It does describe it for the locally finite case because of some TCT, and that means that we can derive some terms that we can derive a Marcev condition that describes HM for the locally finite case, but we don't know whether this is true for general varieties. And that I have a complete variety, I think, that needs to be looked at, because we have tried out some Hobby-McKenzie terms, and I believe for 3-ary and 4-ary terms we could, at least for the examples we tried, we could prove that this holds. But for the certain 5-ary Hobby-McKenzie term, then I can do nothing. So it's very possible that this is also a case when the locally finite and the general case are different. So yeah, I'm absolutely out of time, plus 5 minutes. So thank you very much for that attention. And this was it.
Thank you very much.